Okay. So just...
Do we start?
Yes, we do. Just let me put on the camera.
I put the slide as such. Yes, it's better.
Let me introduce you at first. Well, hello, ladies and gentlemen. Welcome to our next engineering seminary at the CPK PAN. Today we have a pleasure to hear the lecture made by Professor. Oh, yeah, I'm very sorry. It's not this. Made by Professor Marie-Catherine Palau. Probably I did pronounce your last name wrong, so please correct.
No, it's okay.
An engineer and researcher specializing in the design of optical instruments for the space applications. Professor Marie-Catherine has authored scientific publications on the Association of Spacecraft for polarimetric and imaging investigator on the corona of the sun, koronografu, which is part of the European Space Agency mission Proba 3 that is right now orbiting the Earth, and we're also very proud about it. Well, the Association of Spacecraft of Polarimetric and Imaging Investigator of the Corona of the Sun is an externally occult coronagraph designed for precise observations of the solar corona, enabling to study of the structure and dynamics. So here we go. Let's talk a little bit about the sun. As we know, we're right now at the sun's maximum, so everything that's going on the sun is absolutely interesting here on Earth. Professor, in your hands.
Thank you very much for this introduction, Evelina. So thank you very much to welcome me this afternoon. I'm very pleased and honored to speak to you this afternoon. Just to give some words about what I did during my professional life. In fact, this presentation has been done through my experience and thanks to the help of Christian Chatry, which is working for TRAD. And so just to give you some words about my professional experience, I was starting working for Dassault Aviation. I was working for Rafale, it is this famous fight aircraft, and I was working on board computer, and we were taking care about the effect of neutrons of this item of equipment. Then I was working for vegetation. Vegetation was a satellite which was in charge about the observation of Amazonia and the forests and the woods of Amazonia, and in fact the effect of the fact that we are putting out some part of Amazonia on the climate. And then I was working on SARSAT. It was a satellite which was the reference for navigation, and it was as GPS now, but it was previously GPS. And it was possible for the people who were on board boat to take information about their position and the meteo, the climates they will have during the cruise. Then after I was in Matra Marconi Space, so it became a European company. And in Matra I took care about essentially satellites. And satellite as observation satellite, so it was called SPOT. I don't know if you know something about SPOT, but it was observation satellite, one of the first of the European Space Agency. Then it was Helios and a lot of geostationary satellite that Meteosat and so on. And as well on launcher, as Ariane 5. It was the first launcher for which we took care about radiation effects on the item of equipment, almost on-board computer and inertial system. We will speak about that. Then after I joined Aerospatiale, which became Airbus, and in this company. I worked a lot about Ariane 5 to define what was the mitigation aspects for electronic item of equipment, and a lot of satellite as well. We will check later on. So as you know, now we will start the presentation. As you know, we are belong, so everything in what I will told you is related to ionization effects. In fact, when you consider the natural radiation environment, we speak about ionization effects. So twice type. First of all, it is gamma ray coming from the deep radiation space, other galaxy, solar system, galaxy, and so on. And so the point is that this ionization effect, through the interaction about the particle or the ray, gamma, X-ray, is modifying the bias of a component. Might be as well bipolar component or MOS component. We will say that later. So remind that everything I will talk about you is related to ionization effects. So you know that we are in the Milky Way. And so this Milky Way is our galaxy. So a lot, thousands and thousands of solar system. So the closest galaxy is Andromeda. You might know that. And so there is a lot of particles we are speaking today, which are coming from deep space, so galaxy and other galaxy outside this galaxy. So, as I was telling you, we are in the solar system. So there is several planets in the solar system. In between the Sun and us, we have Mercury and Venus. Then after we'll have Mars, will be the next way to explore space. Before we had the Moon, and I must admit I was absolutely amazed by the way the conquest of Moon, if we can call that conquest, but the exploration of Moon was taken during the 70s. Unfortunately, some money was missing and there is no way longer, but it was teaching us, if I can say that as such, about the environment of Earth. So, okay, but the main sources, one of the main sources of our environment is Sun. After galactic rays, they are coming from everywhere. So, solar flare. If we speak about Sun, in fact, there is two aspects in Sun. It is regular rays, I would say, essentially protons, essentially electrons, for sure. But there are events which are extremely important for our in-space objects, launcher and satellites, which are called solar flare. You might know solar flare. And so so there is two items which are concerned by, which are identified by solar flare. It is Earth observation and launcher. And so I was involved in the solar flare when I was working on Ariane 5, because you can see some animation of the Sun, and you see there a solar flare. So it is ejection of particles and mass outside the Earth's environment. And you can see that this ejection is going out of Sun environment. And so you see here more solar flare and the way, in fact, we speak about arch. In fact, when you have a solar flare, you can see some arch. And if the arch is cut, you will have ejection of mass and particles outside solar environment. And we are concerned by that. So when I was working on Ariane, the launcher, the European launcher, you might have heard about that. Now we are in Ariane 6, and I think the situation is the same. We might observe if there were some solar flare just before, because during the launch we cannot do anything. But if some solar flare occurs 20 minutes or 10 or 20 minutes between the launch, we might be allowed to interrupt the launch. So there was not such solar flare, but we were working with NOAA. You know, it is the association in America which is working on environment, generally speaking. And so we were working with the spectra coming from Boulder, and we were observing those spectra just before any launcher, in order to see if effectively there was some danger for the onboard equipment, of Ariane. So you see Sun-Earth interaction. So you have our sun, our star, and Earth, and there is some eruptions, so some flare, which are directly regarding Earth, and there is other one which can be situated in the hidden phases of Sun, which could be interacting with Earth. And for those hidden flare, we were a bit embarrassed, because it was extremely difficult to plan everything regarding Ariane. So now we are going to magnetic field. I didn't tell you, but you might know that Sun has some magnetic activity. So about 22 years, twice 11. And so during this magnetic life, you have 2 periods of maximum activity and 2 periods of minimum activity. Nevertheless, it doesn't mean anything, because you can have serious solar flare during minimum activity. It happened, and so that is the reason why we were always looking and checking the Sun activity. Either it was minimum or maximum before the launch of Ariane 5. So it is for Sun. And you know as well that the Earth have a magnetic field. And you will see later that this magnetic field has an action of protecting the Earth regarding any radiation effect related to outer space. And that is the reason why when there was this observation of Moon, and those missions to Moon, it was planned to build Moon stations inside Moon, because Moon has absolutely no protection regarding galactic or Sun ray. So if you check what is the magnetic shielding for Earth, so you see the sun with its activity, a lot of ejection of mass, electron, proton, and so on. And you will see what is the action of this magnetic field related to Earth, which is protecting the flash coming from Sun from the surface of Earth, except the polar horns. So you check, you can see during the animation the way the magnetic shielding is reacting against solar flare. Essentially, the galactic rays are coming anyway. And so you can see, I don't know, what is the horn, solar horn. So it is here polar, north and south. And so, as I told you, in fact, our launcher was involved by this horn because they are coming from Guyana. if I speak about Ariane 5, which was launched from Guyana, so somewhere here, coming from the north, from the south. And so they are involved in what we called solar horn, polar horn. So here you have some illustration of Earth's magnetosphere. I imagine you know that. So you have the solar wind. The solar wind is essentially electrons, but protons and heavy ions coming from solar flare. And so the Earth is there. And so you have a lot of, so you have this part of magnetosphere which is blocking the ray coming from sun, and so those parts of magnetosphere were interacting regarding the effects of sun and galactic ray. So never forget that there is two parts which are interesting us for the except magnetosphere, two parts which are regarding us. It is solar and galactic ray. Then after you have this famous Van Allen belt. So Van Allen, for what famous gentleman working on the topics during the 19th century, 20th century. And so he discovered the attraction of particles close to the Earth. So there are two belts of electrons and one belt of protons. And we are interested by both of them. Electrons will interfere with the total dose aspect, and protons will interfere with the single event aspects. So you have here in front of you some representation of Van Allen belt. Just, you might know that, but it is interesting to see it. So here you see the movement of particles inside the, where it is there. Inside the Van Allen belt. So you see there is three: movement, oscillation, translation, migration. And so those movements are still under study because it is extremely difficult to define what are exactly the movement of those particles, proton, electron, inside the magnetosphere. So it is important when upon some event coming from outside. So what we will see now is the solar flare. I was speaking about you. I was speaking with you a bit earlier. So here I come back to the fact that Earth has some specific magnetic field. Those you have this magnetic field which has not the same axis that the rotation axis of the Earth. There is some 6 or 7 degrees. It appears that this angle is modified a bit along the time. And so there is a lot of experience and modeling which are showing that this is modifying. And it is the reason why some belts are closer to the Earth than some other one. And for Ariane 5, for instance, so Ariane 5 was launched from Guyana, somewhere here. And here. And we have just close Guyana, some area which is called South Atlantic Anomaly. And when Ariane 5 is launched, it is going directly, I don't remember, it is 600 kilometers, directly to proton belt. And for the component, it might induce some specific vulnerability. So this experience, so I think that regarding our Earth and most of the mission we had inside, that is to say, the solar, when you see the launcher Ariane, so she's coming from there, she's going directly to the South Anomaly. when you are considering observation satellites, so they are coming directly where to the south or the north, it is so south or north, and so they are directly seeing the particles which are coming from galactic ray, so heavy ion or protons, and solar flare for sure. And so you see that for what is geostationary satellites, they are almost in proton belts, the second one. So proton and electron belts, the second one. So if we can resume, launcher, it is proton vulnerability, and then heavy ions, where they are coming to the south or north magnetic pole. For the Earth observation satellite, it is essentially the belts during their way around the Earth, and as it is observation satellite, the poles, north or south. And for the geostationary satellite, it is essentially the mission inside the belts. So just to show you what can happen when there are solar flares, or exceptional even from galactic rays. But what we observe is essentially solar activity. So you can see how the belts, so you see proton 1, electron 1, how they can be modified related to solar flares. So this solar flare coming from October and November 2003 were really the main one for which we had some events. So recently, last year, there was the same type of event and the same type of modification of the belts. For the time being, we have not modelization of those activities. So this series of solar flares induced interruption of electricity in Canada and south and north and south of Europe, so North Europe, South Africa and America. So there was a lot of difficulty related to electricity due to this solar flare, which was during 2 or 3 months. So it was really difficult period for the people who were living in that area. Then we can speak about, so we were galactic rays, solar flare, Van Allen belts, and then we have some activity lower created by the interaction between galactic ray and the atmosphere and different part of atmosphere. And when you consider, so you have the altitude here, 30,000 meters, 20,000 meters, 10,000 meters, and here you have Concorde. So perhaps you don't remember what was Concorde. It was an hypersonic plane created by France and British nation, and it was flying some times ago. So it was a civil aircraft. Now we can have military aircraft at the same zone, and they are affected by the interaction between solar flare or galactic rays with the atmospheric section. And so you can see some particle appearing from this interaction, which is neutron, pions, muons. And I remember to have performed a lot of experience, a lot of tests of the component related to muon and pions in Russia. It was in Gachina, and I was experimenting tests on component due to those particles and subparticles, I would say, because they are existing through interaction. They are not existing alone. They are interacting through interaction. And so we were working on Concorde. And then after, when Concorde disappeared, poor of him, we were working on Airbus. And we were working on the Airbus and some plane coming from Sweden. And so we had we have induced in those planes some experiments which were defining the number of neutrons met during the flight of the planes. This neutrons, it is neutrons, so it could be understood as neutral, but it is creating inside the component secondary reactions. So a neutron can create inside the component a nuclear reaction which is created ions or protons who could give birth to some single event. So I was working on that when I was in Aerospatiale becoming Airbus, and effectively I was working on Airbus 380 on that topics. So is there any question about this presentation regarding environment? No? Oh, okay. So to come back about the effects. So as I told you previously, in fact, there is two main effects regarding the space environment. So two aspects. So first of both, it is total dose effects, which are created by essentially gamma ray, some X-ray, but most of them are created by gamma ray. And so those gamma ray are given effect to are causing some drift in the critical parameters. That is to say, a bipolar component or most component will be affected by the fact that the ionization is changing, and if it is on the on aspect, it can become on the off aspect. So there is, for bipolar, there is drift from the threshold. For MOS, we will come back to that. There will give some modification of the polarization of the component, and anyway, there will be failures, which can give as well permanent failure or abrupt failure. So for total dose, it is permanent failure, and in fact, there is some way to mitigate this aspect. That is to say, under a mission, you can stop the components which are not used, though you stop the bias, or there is damage inside the component, and for that it is extremely difficult to mitigate. So there will be a process modification in order to create mitigation. So it is for ionizing aspect related to total dose. I must just insist on the fact that total dose is almost pointed for long mission aspects. In fact, for satellites, for some satellites, or for the launcher, we don't speak about long dose, total dose effect, because the total dose effect are known till a very long time. So it has been taken into account at the process level for the component. So the point, in order to avoid this type of shift, is to work on the process and the doping process of the component. So it has been taken into account as, I would say, the general process. For single event offset, is it a bit more difficult in the way that it is instantaneous? You have a particle which is choking the component, and the ionization process will give a modification of the state of the cell. And so regarding software, the effect is immediate. I would say it is instantaneous. So the point is that those two aspects are taken into account for sure, almost for total dose, it's very long mission, because for the geostationary satellites, it is 10 or 20 years of mission. So during those 10 or 20 years, you will take into account the total dose, because gamma ray are still there. And for the single event effect, in fact, you must take into account any effect who could arrive. And the mitigation is much more, I would say, specific. And it depends about the function of the item of equipment and how can I say that? The importance, the vulnerability of the system regarding this item of equipment. I remember that we check on the board computer and the inertial system on Ariane 5, and so we put, we'll see later, we put the whole system in front of the beam in order to check what was the sensibility. And we were obliged to change the memory of the inertial system because it was not compatible with the mission of the launcher. So just some information regarding that. So to come back to total dose, to summarize what I was saying, total dose, total integrated dose, the ED, is a long-term degradation of electronics due to the cumulative energy deposited in the material. So it is essentially parametric failure due to shift of threshold voltage or variation in device parameter, as I told you, leakage current and functional failure. So you have anyway trapped electron, trapped proton, solar proton, and gamma ray. So there is several sources to this effect. And then you have damage. And damage those defects, it is long-term degradation, so either parallel to TID, but you can have defect in the crystal of the semiconductor, and it is much more difficult to mitigate it. So there is a lot of there was a lot of simulation which were done in order to avoid such type of degradation, which are remaining. But a lot of you must know that after a lot of 30 or 40 years of simulation, the process of component has fundamentally changed and be better and were improved. So just to tell you what we did for total dose radiation effects. So the point in all those missions is to elaborate what will be the sensitivity, if I can say as such, vulnerability of the component regarding an effect. So for total dose, we were used to irradiate a component in front of cobalt-60 sources. And so you have the component in the situation it will be during the mission in front of the ray, of the X-ray for X-ray, cobalt-60 ray, gamma ray for us now. And so checking the parameter of the component, we are able to see what will be the behavior of the component in space and to put some mitigation aspects. So first of all, we can filter. You observe two components in front of the beam, and so you will see what will be the better. So it is filter. But sometimes you have not the possibility to filter because you have only one for one mission. And in this situation, you will check what are the possibility to have this component better, harder. We can speak about hardening if you want, harder in front of the environment. And for that, regarding total dose, as I told you before, you will have hardening of the process, that is to say doping essentially, and dimension aspect. And when you are on mission, you can decide to stop the bias of the component during some part of the mission is not request, and then come back to bias later on. You might know as well that, in fact, the low dose rate is much more aggressive than high dose rate. There is some, how can I say that, some better life regarding high rate dose, that low dose rate. So sometimes when you are in a mission for a long time, I would say geostationary orbit, satellites, you will be more in difficulty than for a solar flare. A solar flare, you will have a very high dose rate irradiation, and then after it will be better. So you have some, how can I say that? The component is curing in itself. So it's less critical when you have high dose rate than low dose rate. So you will have some information regarding that in some articles. I would like to invite you to be close to nuclear science, radiation effect on composite and radiation effect on component in system, RADEX and NSREC, and you will have a lot of detail and a lot of information related to what I am talking to you today. You will have a lot of more information. When you consider radiation-induced charging of gate optic, this is what I told you recently before, on N-channel MOSFET. In fact, the point of SEU, I would say, or SMU, single multiple offset and single upset, single event upset. In fact, the point is that you have a CMOS structure, and you have two N transistor and MOSFET, I would say, which are blocked. So you have your cell. When you get some ionization radiation, the gate can be, the oxide under the gate can be changed, and except to have N, if you have biasing N, you can become P plus, because the ionization charge is growing. And so your MOSFET, which was blocked, will be deblocked. And for a CMOS cell, you will have an information which is 1, we can become 0, we can become 1. And for a soft program during a mission, it is really a critical aspect, because your program can be changed, as well the nonce, as well the data, as well the instruction. So for us, regarding onboard computer and inertial system, I speak about Ariane 5, but it was the same for the other mission, as well aircraft or satellites. It is really, really a trouble. So I already speak about effect in bipolar devices. So you have essentially the trapping charge trapping, I would say, will change the threshold voltage, and so you have a gain degradation, and for sure leakage, and for sure the failure in the function of the bipolar device. So I invite you to go to Oldham and McLean. This article in NSREC, even if it is old for you, I imagine that it is really the basis of understanding of effects in bipolar device. Single event effect. So we already speak about that. So single event effect, when a single ion strikes material depositing sufficient dose ionization through its prime strike, or secondary particle can occur from the strike. It is what we observed in aircraft due to neutron. The neutron didn't do anything because it is neutron, but they are creating a nuclear reaction, which are giving ions or protons who can cause an effect on the device. Generally, a soft error occurs when a transient pulse or bit flip occurs, and it can cause an error detectable at the device output. So you can imagine that on the item of equipment, you don't see the error at the device output, but you would see an error in the software and in the function of the equipment. So it can be extremely difficult to check what will be the mitigation. Then after, so we speak about single event effect. So when you consider a single event effect, you have clear possibility of mitigation. You know, when I was working on plane, on an Airbus, you can have 5 onboard computer. So if there is some effect, on 5, you will see that there is one which is not working, and it is not given the same that the 4 or the 1. And so you will choose the 4 or the 1. The fluence of neutron at 14 kilometers is not so important. So it is extremely difficult to have 2 or 3 events on the plane at the same time coming from the neutron. So 5, 3, 2. So it is easy to make a vote. For Ariane 5, we had only 2 computers. So there is one computing. If the computing of the 2 computers was the same, no problem. If it was not the same, so it was the majority which was taken. So 1 vote. If the vote of the 2 computers was not the same, we come back to another vote. And then after, we can imagine what was the solution. So for the soft error, and it was the same, so I speak about the aircraft and Ariane 5, but it is the same for the satellite. You can imagine some mitigation based on the comparison of the output of the equipment. But after, you can have the single event effect, the soft one and the hard one. And the hard one, what we had in mind, and what was the most dramatic, I would say, was single event latch up and single event burnout. You have a lot. We will see later on the number of single event we have, but single event latch up for transistor and single event burnout for MOSFET was extremely difficult. Just to give you some history regarding those effects, it was reported for the first time in 1975 by Dr. Binder. And then after, it was seen on mission. So 1978, 1985 on Pioneer 12. And I was working on Spot 1 in 86, and just a point. So we were testing the memory on the onboard computer of Spot 1 just before the launch, for sure, and we saw that it might be difficult, it might be delicate to put those type of memory on board. But, you know, it is industry, it is life. So the manager of the program didn't want to change the memory. It was too late. And so we had those memory on the satellite. And so it was launched in April 86. And in October 86, the satellite was defailer. So he get failures. And it was a bit difficult to admit that what we said before was true. That is to say that the memory was not strong enough, hard enough to support the environment of a Spot, which was, as I told you before, an Earth observation satellite. So it was for Europe. It was the first time it was really critical to have SCU on board satellite. Just to have some word about the way to test S single event. So you see here the setup in Montpellier, Radiac. Personally, I was working in Caen on the Ganil. It is the big accelerator for heavy ions in France. And then I was it was for heavy ions. And for protons, I was to Paul Scherrer Institute. So we were testing component during the night, and people was cured for cancer, leukemia during the day. So, you know, good exploitation of a mean, of a test mean for health and for component. So to come back to the way to test the component, just a few words about that, and then after, I hope you will have some time for question. If I cannot answer to the question today, I will answer you later on by mail. So to test component regarding SCU, so you must expose the component in front of the beam, a beam of heavy ions, of protons, regarding the linear energy transfer, the range energy, the counting events, and the cross-section of the component. In fact, you have several ways to simulate the number of SCU in space regarding to their sensitivity and the environment. I was working on Spacecraft. I think it is still existing, but it was the first one. And so in order to know what was the sensitivity of the component in an environment, we had to put inside the linear energy transfer and the cross-section in order to see, related to the environment, what was the sensibility of the mission. It was what we do. Now there is Homer. I will send you, if you are interested, by, perhaps you already know, Homer. Is another type of soft to simulate. And but anyway, it is taking into account the same way to illustrate, I would say, the component. That is to say, linear energy transfer and cross-section. And there is, as I told you previously, a lot of SEE. And for us, when we were on site, in fact, the most important were SEU, single event offset, MBU as well, because when you have an so you imagine a proton or neutron taking, having an interaction with an atom inside the component, you can have another effect induced by the first one. And so for the very, very fine, I would say, very, very small integration, you can have MBU, multiple BIP upset, as well for proton, neutron, or heavy ions. And what was concerning, we were dedicated in the examination of SCU, so single event upset, we spoke about that, single event transient, because in fact, you can have some particles which is interacting and which have not a permanent at the level of electronics aspect, but just, I would say, a step who can be taken into account by the system as a wrong state. Then you have single event latch-up, we spoke about that. Single event burnout, so it is for MOSFET, and gate rupture. So for gate rupture, it is very, very difficult to do something because it is, you cannot do, it is destruction of the component. So just some aspects. So when you irradiate a component in front of a beam, you have the notion of linear energy transfer, which is related to the type of ion or proton. For proton, we speak about energy. For ion, we speak about linear energy transfer. Then you measure the cross-section. You have the cross-section, so you have, when you use an accelerator, you have different type of ions. And so at the very beginning, so you consider, you see that there is no event related to the energy of the ions, the first ion. Then you go through the different energy of the ions. And at one time, it is what you see here, you have the cross-section which appear. That is to say that the for some type of heavy ions or protons, it depends on the energy, you will have some sensitivity of the component. And you have as well the notion of sensitive volume. That is to say, it is the volume which is responsible for charge collection, which will give to an SEE. So it is, it is basic aspect. I must imagine that you know them. So to come back to what I was saying before, you have a lot of, you have some classes of SEE. So soft error and hard error. I won't list because I already did it. The types of, now perhaps I don't think there are more, but there are a lot. So we have to take care about all those ones. We speak about a single energy, single upset. And to come back to the hardening method, in fact, it's just a summarizing of what I was saying to you before. So for the transistor, depending on the type, it is specific technology. So it was what I told you, specific doping for the transistor, or specific biasing. So you can imagine that you will have, according to the application you will have with the transistor, some type or some other type of biasing. And for the SEE, so by the past, we work about silicon on sapphire or silicon on insulator. And in fact, it still existed, but it is very specific technology, very, very expensive. So we prefer now to speak about design hardness, that is to say, EDAC, so correction and detection error, and majority voting, lack of bias under aggression, it is what I was telling you, or recovery items. So it is only such. So to come back to conclude of what I was saying to you, so there is a lot of events, a lot of effects which can be given by radiation, environment, on the component and on the equipment, item of equipment is space. And really, it is a way to study what will be the vulnerability of the equipment. You can imagine that for some phases of the system mission, if you have some vulnerability of some item of equipment, it won't have any problem regarding the equipment, the system equipment. And but for some phases, we saw that during we saw that when we were working on Ariane 5 during the launch, all the main equipments as inertial system and onboard computer are extremely important. And so it was not caused by environment, radioactive environment, but you don't remember, but there was some real critical event on the 4th of June 1986. It was the first flight of Ariane 5, and it was a failure. It was, and the fact is that we experiment Ariane 5 regarding to Ariane 4. And so there was the same item of equipment on Ariane 4 as it was on Ariane 5. But the propulsion system of Ariane 5 was much more efficient. And so the way to take in account the data was much more quick, rapid on Ariane 5 and Ariane 4. There was a failure on one of the onboard computer for Ariane 5. It was given to the other computer, and both of them cannot compute it, and so it was a failure for the launcher. So, in fact, the mission of a system is related to the item of equipment, and we must be very careful in the way we use the item of equipment, and it is really characterization of the component and the functions of this component. Okay, so it's finished for me. I hope you follow everything. If there's some question.
All right, so thank you very much for the remarkable lecture. And right now, do we have any questions from the floor or perhaps from the viewers?
If you have not now, you can have later. I will answer later.
Well, do I see anything? Is there a chat? Well, right now I don't see any questions.
I have a question.
Oh, you have a question.
Thank you.
I have a question. I will write you a little bit more details, maybe through the chat, because I don't know if that could be patented or not. I don't know. But how you are seeing possibility for using hydrogen as some kind of shielding for radiation?
You speak about shielding regarding mitigation?
Yeah, according to the radiation that we have in space, we can use the hydrogen is quite a good solution. That's why the water is in use. But how you are seeing a solution in which you can use some kind of material that could be
for sure.
That could be saturated with H2.
Okay, so the point is with shielding, so we use shielding to protect component for sure. It was essentially for those rates because the heavy ions, the protons are very efficient and they can go through shielding. It must be really computed, and the point is that when you are adding shielding, you are adding weight. And so we did some experience with, we protected only component, not item of equipment. So we have specific shielding. It was essentially for total dose, close to the component which was sensitive. What we imagine as well is to organize the equipment in order to have sensitive component inside the equipment. That is to say, with several layers, I would say, of protection between environment and component. So yes, we did that for sure. But the point, and we already do. The point is that we must pay attention to the fact that we have not to add a lot of weight to the equipment because we have to launch it. We have to put it in space. But yes, we did it. Sorry, perhaps I didn't speak about that, but yes, we did it. And we do it.
Okay,
we speak about titanium. We had a lot of protection with titanium.
No. I wrote some short information in chat. Yeah, thank you very much for the.
Do you have any questions? I will transfer.
Okay, I will send it through it.
Professor.
Yeah, I will send it.
Yes, you can send me some further information if you want more specific.
Yeah, because
answer for sure.
It's a design that have to be consulted with an expert.
Yeah.
In order to eliminate any kind of errors in it. Thank you very much for your answer.
Thank you for your attention. Thank you very much.
So I put down my email address for all of you who would like to ask some questions of Professor. And of course, I will transfer all of those questions to you. asking you.
Thank you very much.
Kindly
I will answer for sure.
to answer them.
And I can, for sure.
I'm sure I can.
Okay.
You have such a remarkable life and work experience that I'm sure you can. Well, if there aren't any questions, I can say thank you very much, Professor.
Thank you to you for the attention and to take into account what I said. Thank you.
Thank you so
much. It will be a pleasure to have another intervention, for sure.
Wonderful.
Bye-bye. Thank you very much, Evelina.
We'll stay in touch.
And all of you. Thank you. Bye-bye.
Goodbye, thank you.
Bye-bye.